last lecture, we learned how to calculate the condensation energy as the difference between the ground state energy of the BCS theory of a superconductor and the energy of the normal state. That difference gives you the condensation energy. Of a BCS superconductor. At 0 K. We learnt that WBCS 0, which is the ground state energy of a BCS superconductor at absolute 0, is summation over all k psi k into 1 minus psi k by E k minus L cube delta square by V 0, where E k is given by psi k square plus delta square, and delta is the energy gap parameter defined by and the normal state energy W n 0 is given by because only states up to the Fermi energy are filled in the normal state, and psi k square, psi k is h cross square k square by 2 m minus the Fermi energy at absolute 0. So, here we also use the parameters V k square, the occupancy factors were given as half of and this is 1 minus. Using these, we can calculate delta E, and in order to do that, we split the summation into two parts. Here we can write this, and the normal state is just has this energy. So, this for U k square is 0 for energies less than E f 0 minus h cross omega d. This is because for such energies in the gap, if this is E f 0, this is E f 0 minus h cross omega d, and this is E f 0 plus h cross omega d. Now, for states below this, all states are occupied. So, they are all occupied states. Therefore, V k square is 0, V k square is 1, and V k square is 0 for E greater than E of 0 plus h cross omega d. That is, these states are all empty states. So, V k square is 0 for them. Using this, we can simplify delta E, and we go from L to the power minus 3 summation over k to 1 by 4 pi cube integral dk. In other words, we convert the summation into an integral. Since the states are all almost quasi, it is a quasi continuum of states with a density of states function. Using all this, and we also use the energy gap expression, delta can be shown to be minus V naught n of E of 0 by L cube integral So, this can be readily shown from this definition here using the expressions for V k and U k. So, using all this, we can show that delta E, the condensation energy at absolute 0, turns to be so that these two cancel, leaving out a particularly simple expression. That is a very remarkable result, because physically it means this. This means that the condensation energy of all the Cooper pairs in the superconducting state of a BCS superconductor at absolute 0, in other words, all the electrons, all the conduction electrons pair up, and how many electrons are there? The number of electrons is given by the density of states times the width in energy, which is the order of energy gap, and this is the number of electrons. You have to take half this in order to find the number of pairs, and this number of pairs in an energy interval delta. Therefore, if each of them has a binding energy delta, binding energy of a pair is delta, then delta E, the condensation energy, is just the number of pairs times delta, which is delta square, which is the result that we have here. So, we have a simple physical interpretation for the energy gap parameter delta, which is as just the binding energy of a Cooper pair at 0 k. So, this has a very important physical interpretation in the sense that this says, this is one of the important results of the BCS theory, that a gap opens at the Fermi energy and its magnitude is of the order of delta. So, this is the physical interpretation of this. So, there is an excitation spectrum where in the normal state all these states are filled and all these states are empty. Now, at the superconducting transition at absolute 0 of a BCS superconductor, there is a gap which opens symmetrically about the Fermi energy, and therefore, this is minus delta and this is plus delta. So, this is the gap and no states are allowed here, and this explains the reason why there is an excitation energy of the order of 2 delta which is needed in order to excite electrons from these occupied states into the gap, explaining the exponential temperature dependence of the specific heat of a superconductor at low temperatures. This also explains why in tunneling experiments we find that there is no current in the IV characteristic until we reach the energy of the order of the energy gap, then there is a current. So, this is the IV characteristic of a superconducting tunnel junction. So, and this also explains why the microwave absorption as well as the ultrasonic absorption shows that there is an excitation energy of the order of the energy gap. These are all important results of the BCS theory. Now, let us just go back to this gap parameter, the definition of the gap parameter, and try to get an expression for this. So, we see the delta is from what we have given half V naught by L cube sigma k delta by E k, and this gives the condition 1 equal to V naught by 2 integral minus h cross omega d to plus h cross omega d n of E f 0 d E by E square plus delta square to the power half. Therefore, we get 1 by, if the density of states is slowly varying with respect to energy, then we can factor it out of the integral and write 1 by n of E of 0 V equals integral minus h cross omega d to plus h cross omega d delta E by E square plus delta square to the power half, which integral is known to be sin h inverse h cross omega d by delta. So, turning it over, we can get an expression for delta as h cross omega d by 2 sin h 1 by n of E f V. And since n of E f 0 V, if it is very small compared to 1, which is the condition known as weak coupling, the electron phonon coupling is weak and the attractive interaction bringing about the superconducting transition is rather weak. In that limit, delta can be approximately written as 2 h cross omega d exponential minus 1 by n of E f 0 V. So, that gives the expression for the binding energy in terms of the electron density of states and the electron phonon coupling. The pre-exponential factor is not very important except to show that it involves a phonon mechanism and hence involves the Debye frequency here. So, this is the parameter which strongly determines the value magnitude of the delta, and therefore, we know that a material with a large electron density of states at the Fermi energy is likely to have a larger delta, and similarly this is also connected with the strength of the electron phonon coupling constant. We have so far discussed the BCS superconductor and its behavior at absolute 0, but what is of real importance is what happens at finite temperatures. When one goes to finite temperatures above 0 Kelvin, we have 1 by n of E f V very similar to this, becomes again minus h cross omega d to plus h cross omega d of this integral d E but there will be a temperature dependent factor because of the statistical occupation, and that is given by 1 minus 2 f of root of E square plus delta square plus E of 0. This is the f is the Fermi Dirac function, well known to us from the conduction electron theory, and f of E is 1 by exponential E minus E f by k b t plus 1, and we have here Fermi Dirac function describes the probability of occupation of an energy state of energy E by an electron, and the factor 2 in front of f of this function is because we have a pair. So, you get the probability is doubled, and the probability that the state is empty is 1 minus 2 f, and therefore, substituting for this Fermi Dirac function and then calculating this, we can find the temperature T c at temperature equal to T equal to T c, the energy gap vanishes, because the energy gap is now the order parameter of the superconducting transition, and at the superconducting transition this energy gap opens up and becomes non-zero. About to the superconducting phase transition, the gap becomes 0, it vanishes. So, the energy gap is the order parameter of the superconducting transition. So, the superconducting phase transition temperature T c is defined as that temperature at which the energy gap vanishes. So, from this expression we can find the condition for delta to vanish. In order to do that, we have to evaluate this integral. So, we get 1 by n of E f V equal to that is from this and this definition. Therefore, evaluating this numerically, we get 1 equal to n of E f V times log 1.14 h cross omega d by kBTC. That means kBTC equal to 1.14 h cross omega d exponential minus 1 by n of E f v. This 1.14 is the result obtained from numerical integration of this integral. Therefore, comparing these two, we can write the ratio of kBTC to delta as 1.14 by 2. Therefore, this is delta 0. In other words, delta 0 is kBTC times 2 by 1.14, which is 1.764 kBTC. So, this is another important prediction of the BCS theory at finite temperatures for the superconducting transition temperature. The superconducting transition temperature is given in terms of the energy gap at absolute 0 by this factor 1.764 kB. So, that is a very important prediction by this BCS theory, which can be experimentally verified for superconductors whose superconducting transition temperatures have been measured and whose energy gap can also be measured by the techniques that we described above already. Therefore, this gives a very nice way to test the validity of the BCS theory. So, based on this, the superconductors have been classified as weakly coupled superconductors, strongly coupled superconductors in which the BCS theory is not obeyed, and intermediate coupled superconductors. So, this is in brief the microscopic theory of the superconducting phase transition, which accounts for the superconducting phase transition as being brought about by the formation of Cooper pairs by the conduction electrons in the Fermi sea of a normal state superconductor. So, that gives in brief the basics of the BCS theory, and we now pass on to another important class of phenomena connected to the superconductors, namely the Josephson effect. Or the Josephson tunneling, which was a phenomenon which was discovered by Josephson, and this describes the coherent tunneling of a Cooper pair across the gap between two superconductors. Crucial to understanding this is the idea that a superconducting state is quantum in nature, and a given superconductor, it is a macroscopic quantum mechanical state with a wave function which is given by where rho is the charge density and theta is the phase factor. So, theta is the quantum mechanical phase factor, which is given by, as we already saw, as the line integral of this factor. This is very important because we are describing the tunneling of Cooper pairs in a coherent manner from one region described by one wave function across a barrier into another region described by a different, not necessarily the same, quantum mechanical wave function. So, this is similar to the tunneling of carriers across a gap from one quantum mechanical system to another, which is well known in quantum mechanics. So, the results are easy to describe, and the importance of this effect is that this provides yet another means of observing Cooper pairs and the macroscopic effects produced by them in superconductors. In particular, enables us, because the line integral A dot dl over a closed loop is related to the surface integral del cross A dot ds by Stokes theorem. And del cross A is nothing but the magnetic induction, and the surface integral of the magnetic induction is what we understand by the magnetic flux threading this contour, this loop. And this, as we saw already, led naturally to the quantization of magnetic flux in terms of the fundamental unit of the flux quantum, which is h by 2 E, where E is the electronic charge. So, this is the flux quantum. Josephson tunneling enables us to observe and measure this flux quantum by forming a tunnel junction made of two superconductors and observing the tunneling current produced by the passage of these Cooper pairs across a barrier separating these junctions. So, this is known, this forms the basis of what is known as superconducting quantum interference device. So, this is known as a squid. A squid is a superconducting quantum interference device, which basically consists of two superconductors separated by a barrier. This barrier can be a normal metal, can be normal metal, can be an insulator such as an oxide, and so on. So, it can be a weak link between two superconductors also. So, such a the Cooper pairs tunnel across this gap from superconductor S1 to superconductor S2 in a coherent manner, so as to preserve the quantum coherence. So, we are able to measure, in the presence of an applied magnetic field, we are in a position to now manipulate the quantum phase difference, the quantum mechanical phase difference between these two superconductors. The situation here is almost similar to the Young's double slit experiment in optics. In which you have two slits and the light is transmitted across them, and then the intensity of light is measured on a screen. So, you have two slits and the light goes like this and then converges onto a screen here, and this is the screen, slit 1, slit 2, and the light is coherent light is passed through this, and the intensity distribution, they are allowed to interfere constructively on the screen, and the intensity distribution here is measured, and that is a function, the intensity distribution is a function of the phase difference between these two waves which go through the two slits. So, this is the essence of the Young's double slit experiment. We have a complete analog of it. So, instead of the two slits, we have two superconductors, and they the pairs pass through this, and then you measure the current across this tunnel junction. So, you measure the Josephson current, which is the tunneling current across these two superconductors, which is now just like the intensity on this screen. This tunneling current is a function of the phase difference between these two quantum mechanical systems formed by the two superconductors, and this quantum mechanical phase difference is a function of the applied magnetic flux. Therefore, by controlling the varying the magnetic field applied, one can control this phase factor and therefore control the Josephson current. So, by observing the intensity distribution maxima and minima in the Josephson current, one can link it to the applied magnetic flux, and therefore, one is in a position to actually measure the quantum mechanical phase difference, which is modulated by this, which is produced by this variation in the magnetic flux. So, that is the reason why you are one is producing, one is actually carrying out a quantum interference experiment, just like in the Young's double slit you have a optical interference. So, one performs quantum interference, which is a direct verification of the quantum mechanical nature of the superconductor. Another important reason why the squid is of interest is because the squid enables us, we will write the relevant equations in the next lecture. The squid enables us to measure magnetic flux in units of the flux quantum, which is an extremely small quantity. This is something of the order of 10 to the power minus 34 by 10 to the power minus 19. So, this is about 10 to the power minus 15. The flux quantum which is measured is of the order of 10 to the power minus 15 Weber per meter square, and therefore, this is an extremely small flux. So, one has the possibility to measure extremely small variations in the applied magnetic flux using such a squid. So, this is known as the Squid Magnetometer. So, which measures the changes in the magnetic flux in units of the flux quantum in a very sensitive fashion due to extremely small changes in the applied magnetic flux. So, this gives you a very sensitive method for measuring magnetic flux, and this is a very important fact, because the entire gamut of measuring instruments such as a voltmeter, an ammeter and so on in electrical instruments, measuring instruments, they all are based on the measurement of magnetic flux due to a current. The magnetic effect of a current produces this magnetic flux change, and it is a sensitive magnetometer means an equally sensitive ammeter or a voltmeter and so on. So, the entire process of measuring extremely small currents or extremely small voltages is rendered very accurate using a Squid magnetometer in addition to measuring magnetic flux. So, these are some of the basic applications for Squid magnetometry, and that is what these are some of the practical applications of superconductors. So, the superconducting quantum interference device in one stroke demonstrates the quantum mechanical nature of a superconductor on the theoretical side, enables us to measure the flux quantization, flux quantum, and also provides the basis for an extremely sensitive method of measuring magnetic flux and hence current and voltage. So, this is an application of a superconductor which is of very far reaching in its scope. So, we will consider some of these in the next lecture.